Let's get that going. I think this is on. Yeah. Okay. Quick review of what we ended with last time. So last time, what we were focusing on was relations. Right? Did we talk about relations last time? I think we started with relations. I have it here as a reminder. We talked about equivalence relations. Yeah. Oh, yes, we did. And we went through a concrete example. Okay, yes. We did talk about relations. Great memory. Okay, so we talked about relations. Reminder, what is a relation now? The set theoretical notion of a relation. It's just a set of ordered pairs. So if I say R is equal to 1, 2, 3, 4, there's a relation. It's a set, and everything in the set is an ordered pair. When it's a relation, this is capturing the notion that 1 is somehow related to 2, so we would write 1R2 as 1 is related to 2. Going back to our old logic notation. So this was a notation we used in logic. This is our set theoretical definition now of a relation. We still use that same notation. 1's related to 2 just means that the order pair 1, 2 is inside the relation. Okay. Then we have the notion of a relation from one set to another set. So R is a relation from X to Y if and only if R is a subset of X cross Y. Let's remind ourselves what X cross Y is. It's all the possible order pairs we could make where our first element comes from X and our second element comes from Y. Right? And so if R is a subset, so X cross Y, this is a set of ordered pairs. R being a subset of X cross Y, R would still be a set of ordered pairs, so it is a relation. And it's a relation where all its left-hand elements are going to be in X, and all its right-hand elements are going to be in Y. So we say R relates X to Y, or R is a relation from X to Y. Okay. And then we say R is a relation on X if R is a subset of X cross X. Notice X cross X is going to be all the possible ordered pairs we can make where the first element comes from X and the second element comes from X. If R is a subset of that, then it's relating things in X to things in X. Right?
So is that meant to say R is a relation on X? Or R is on X, not R in on X?
Yes. Wow, I missed a lot of words. R is a relation on X if and only if R is a subset of X cross X. And so if we made something, X could be the people, like the people in this room, and then R would be the is taller than relation. We would have the ordered pairs in there. We would have Parley is taller than Donnie. We would have Parley is taller than Karen. We would have Parley is taller than Emma, etc. We would have I'm taller than Emma, whatever. And we fill in all the is taller than relations. Notice that all the left-hand elements are going to be people in this room, and all the right-hand elements are going to be people in this room. So this would be one possible relation we could create on the set of people in this room. So if X were the set of people in this room, here's one possible relation we could create. Quick question. Is that a relation if X is a set of people in this room?
Yes.
Yes. This is a is married relation for the set of people in this room. None of us are married. Or anything else. Everything in there is an ordered pair. And all those ordered pairs came from X cross X. Or in other words, this is a subset of X cross X. Trivially so. So the empty set is always a relation on your set. Make sense? Okay. So relation from one set to another set, relation on a set. Now, an equivalence relation. Equivalence relations are relations that somehow capture the notion of somehow being the same. Equivalence relations satisfy these three properties. They're reflexive, symmetric, and transitive. What does it mean to be reflexive? It means everything is related to itself. X is always related to X for any X you pick. Maybe this would be better if we kept an example of an equivalence relation in our mind. So we could use, doesn't really work on this room because there's not very many people. Imagine we had a whole school of people. And we could have the R be the is the same height relation. So notice you're always the same height as yourself. And then if you're the same height as George, and George is the same height as you. So it's symmetric. And if you're the same height as George, and George is the same height as Henry, then you're the same height as Henry. So it's transitive. Same height is an example of an equivalent relation. It's reflexive, you're always the same height as yourself. It's symmetric, if you're the same height as someone, they're the same height as you. And it's transitive. If X is the same height as Y and Y is the same height as Z, then X is the same height as Z. One example. Some other examples of equivalence relations: equals on the real numbers. Equals is a equivalent relation. X is always equal to X if X is equal to Y, Y is equal to X. If X is equal to Y and Y is equal to Z, X is equal to Z. We said same height on people. We could use congruence in geometry. Think about it as triangles. A triangle is always congruent to itself. If triangle X is congruent to triangle Y is congruent to triangle X. If triangle X is congruent to triangle Y and triangle Y is congruent to triangle Z, then triangle X is congruent to triangle Z. So a bunch of equivalence relations we could come up with, and it's saying that they're somehow the same. That's what equivalence relations do. They say these are somehow equivalent. There's a way of thinking about these things as being equivalent. Okay, so now a partition on a set. A partition on some set X is a set of mutually disjoint subsets of X whose union is X. What does it mean for what's a mutually disjoint subset? What's mutually disjoint?
Disjoint means that the intersection of any two is the empty set.
Right.
I'm not sure what mutually disjoint means.
So if we have a set of mutually disjoint subsets, that means each element shows up in one and only one of those sets. So again, imagine we had a student body, and we broke them up into the students who went to classroom 1, the students who went to classroom 2, the students who went to classroom 3, the students who went to classroom 4. Each student goes to one and only one classroom. Bob can't be in classroom 1 and classroom 2 at the same time. He's in one and only one of those sets. So if we took the student body and sent them to their 4 different classes for the morning, then those would be mutually disjoint sets. No student shows up in more than one set. Furthermore, if we were to go count all the students in classroom 1 and 2 and 3 and 4, we would have counted all the students. So we partition the students up into all their classes. So here's a partition again. A partition on X here would be the entire student body, is a set of mutually disjoint subsets. Those mutually disjoint subsets are going to be each of the classes they have that morning. So is a set of mutually disjoint subsets of X whose union is X. So if I went and union up all the students in each of the classrooms again, I get back the entire student body. So I partitioned up the student body.
A lot of MySQL having a partition function to break up certain logic and one certain operation on that group.
Yeah, partitioning up data is something you do all the time. Take the data and put it into separate sets. Each data point shows up in one and only one set. No data point shows up in 2 sets if you partition it. You partition, probably have partitioned a computer before and have it run multiple operating systems. What do? You take the memory and you split it. And you say Windows gets to use this memory and Mac gets to use this memory. Or Linux, or whatever you partition it with. So that's partition. Pretty straightforward idea. Let's just remind ourselves one more time. It's a set of subsets. So if A represented all the students in classroom 1, all the students taking, we'll pretend we're at a school, and the morning classes are algebra, history, geometry, some music course. So A represents all the students in algebra, H all the students in history, G all the students in geometry, M all the students in some music class. So Bob might be someone in music. Then the set of all these sets is our partition. It's a set of subsets. And each of these would be a subset of the entire student body. So if X is the entire student body, that's all the students in algebra, all the students in history, all the students in geometry, all the students in music. That represents the entire school body. This would be a partition. Furthermore, we could have come up with an equivalence relation to get this partition. Our equivalence relation could have been, is in the same class. So let's imagine for a second that Bob is a particular student and Bob happens to be in the algebra class. Notice, is Bob in the same class as Bob? Yes. If Bob's in the same class as Jerry, is Jerry in the same class as Bob? If Bob's in the same class as Jerry and Jerry's in the same class as Frank, is Bob in the same class as Frank? So we can use an equivalence relation to partition up our data. And when we do Bob with square brackets around him like this, it means everyone related to Bob using our equivalence relation. This only makes sense in the context of some equivalence relation. So if we already know that our relation R is in same class, then this square bracket notation around Bob would be shorthand for the set of all people in the same class as Bob. And if Bob was in algebra class, then this would be all the students in algebra, including Bob. And if Frank was in history, then when we did square brackets like that, Frank, that would be shorthand for everyone in history.
So that's like equivalent to the set history.
Yes, this would be equal to, in this case, it would be equal to algebra since Bob's in algebra, and this would be equal to H, everyone in history, since Frank's in history. And if Bill was also in history, then notice the equivalence class on Frank is the same thing as the equivalence class on Bill, because they're both in history. So they're all related to the exact same people under that relation. So we can use equivalence classes to build partitions. So now let's read exactly what an equivalence class is. If R is an equivalence relation on X, then the equivalence class, square bracket, some little x out of big X, is a set of all the elements in big X such that they are related to little x. So the equivalence class on little x is a set of all y in big X such that little x is related to y. Everyone they're related to. And you can take the equivalence classes, and that gives you a partition. So anytime you have a partition, you can think about in terms of equivalence classes. Anytime you have equivalence classes, you can think about them in terms of partitions. If there was some method to our madness in how we created our partition, whatever that method was, we just call it some relation, and it's going to be an equivalence relation. In this case, the method to our madness on how we partitioned was we pick people in the same class. Call that your relation, then the equivalence, then it gives you the equivalence classes for your partition. So logically equivalent things there.
If you're writing it out, are you saying that the context is always, or is there a way to describe it in formula context?
You're saying for our relation?
Yeah. Like,
As long as your relation is an equivalence relation, if it satisfies these properties, then if we split it up into equivalence classes, that's the same thing as partitioning up our data.
and I got all that. I'm saying, how do you, in a formula form, specify the context of Bob, for instance? How do you?
So let's say, do a more concrete example. We'll say that X is going to be, in this case, all the integers. We'll make R the has same parity. That means both even or both odd. So 2 is related to 4 because they're both even. 1's related to 3 because they're both odd.
Say parity?
Yeah. And so then the equivalence class on 1 would be all the odd integers. We can't write them all, but it'd be dot, 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 -3, -1, +1, +3, +5, dot, dot, dot.
And so how you would write that out is you actually, so like for instance, your formula at the bottom does not actually specify that it's coming from the partition R. And I'm just curious.
R is our relation, so I can use my relation, since has the same parity, is an equivalence relation.
I get all that.
I can use it to partition up my data.
Mostly a syntax question.
The syntax question.
Yes. As far as how do I know that when you say the bracket 1 is actually coming from R, especially when you're using multiple different partitions?
Oh, it has to be understood from context what your set is, X, and what your relation is. And then using this notation only makes sense if you already showed that R is an equivalence relation. This notation doesn't make sense if R is not an equivalence relation. If R was the is taller than relation, that's not an equivalence relation. Because if you're taller than me, I'm not taller than you. So it's not symmetric. Or you're not taller than yourself.
I get all that. And on the event, you're working with multiple different relations in the exact same notation.
You'd have to come up with notation if you want to do that. So you could probably do something like a little R down there or something, specify.
That would make sense.
But yeah, usually it's obvious from context what's meant. Okay, so talked about equivalence classes and partitions. Same age on students, that's just another example. I think we're good there. Okay, so now let's move to functions. A function is a relation where each left-hand element is paired with one and only one right-hand element. Let me give you an example really quick. If I pair 1 goes to square, 2 goes to triangle, and 3 goes to square again, is that a function? We know it's a relation because it's a set of ordered pairs. Is it a function? But I have 1 goes to square and 3 goes to square. That's fine. What would not have been fine is if I would have put a 2 here and said 2 goes to square. Because now you can't say what 2 goes to. I know 1 goes to square. What does 2 go to? Does it go to triangle or does it go to square? So this is not a function. It's a relation. It's not a function. A function is a relation where every left-hand element is paired with a unique right-hand element. So I have 2 goes to triangle, 2 goes to square. No, it doesn't make sense. But before, when I had 1 goes to square and 3 goes to square, not a problem. I know what all my left-hand elements go to. You can answer the question, what does 1 go to? You can answer the question, what does 2 go to? You can answer the question, what does 3 go to? What about if I put 1 there? Is that a function?
Yeah.
But we have 1 showing up on the left twice. Yeah, we paired them with the same thing. And in fact, remember all the way back that in sets, duplicates don't matter. So this set actually only has 2 items in it. It has this order pair and it has this order pair.
And out of curiosity, in that factor, if there was 2 sets inside of a set that would have the same exact elements, also.
Yes, because remember that this is a set. We're just using fancy notation.
Right.
And this is a set. We're just using fancy notation. And I'm not going to write out exactly what that set is. Actually, I guess in this case it wouldn't be too hard. Actually, it would be hard if I couldn't use 1 and square.
Right. And I was just curious if it nested identical also eventually.
Yep, if you look at the elements, that is identical to that. So this only contains 2 things. All right, so still a function. We can put a 3 there, still a function. If we put a 2 there, it's no longer a function. Now I don't know what 2 goes to. Does it go to triangle or does it go to square? Okay, so now let's read the, oh, that's just a function in general. Now let's talk about a function from x to y. what's a function from x to y? First off, you need to give me the set x and y. But a function from x to y is going to be a function that relates everything in x to something in y without having a particular thing in x go to multiple things in y. So let's come up with sets really quick to get a concrete example. We'll say x is equal to set 1, 2, 3. We'll say y is equal to the set ABC. So then, if I have my function f is equal to 1 goes to A, 2 goes to B, 3 goes to C, this is a function from x to y. If I would have had 3 goes to A, is it still a function from x to y? Yes. If I would have had gotten rid of 3 altogether, is this a function from x to y? No. It has to map everything in x to something in y. So I have to map all of x to something. So I have to use 1, 2, and 3 as my left-hand elements. No choice about it. And then I just have to map them to something in y. Doesn't matter if I map them all to the same thing. That's perfectly fine. If you map them all to the same thing, we call that a constant function. But it's still a valid function from x to y. Maps everything in x to something in y. So now let's read its exact definition. A relation f from x to y is called a function, provided that for every x, for every little x in big X, so for everything in here, there exists one and only one thing in y, such that f of x is equal to y. Is this the first time we're seeing this notation? Are you good with this notation, or do we need to explain that notation a little bit? Let's explain it a little bit. Okay, so let's go back down to this picture. F is equal to this. With functions, since we're guaranteed for any left-hand element, it only maps to one right-hand element. We have this special notation. F, when I do f of 1, that means what is paired with 1? In this case, it would be A. If I did f of 3, that is equal to, again, A with this function. Let's change up our function. Let's say f is 1 goes to A, 2 goes to B, 3 goes to C, 1 goes to B. All right, is that a function? No, it's not a function because we have 1 goes to A and 1 goes to B. So if we were to come and try and write f of 1, what's f of 1? Should it be A or should it be B? We don't know. That's why we only use this notation when it's actually a function. We don't use it with relations, we use it with functions.
Why would you ever just specify the domain of, or the set of y when it could be in everything and still work?
Why do we? Because we care what what the function is relating to. The function is usually mapping from one set to another set. We care about the other set that we're mapping to.
But the fact that you don't technically have to even use everything in the set, you can make it the everything set.
So that would be like, I don't know, whatever language you're used to using in programming. Using the any, if it has an any. I don't know.
Oh.
Whatever you use for, have you ever used a strongly typed language?
Yeah, TypeScript is.
Okay, so you got something strongly typed, and then
TypeScript?
I may have written it before. I mean, and in that language, you have a type that represents any.
So you're specifying the domain of what you expect the output to be for the range of the set.
Right, so you have some function that gives an output. Technically, you could always make the output anything. Why specify it's a Boolean? Technically, it could be anything. Sometimes it's useful to know that actually it's a Boolean or an integer being returned. That's very useful knowledge. So this function is going to be mapping from one thing to another thing. It's nice to know that everything that's going to come out of this function is a real number or an integer or whatever. That's very useful information. And to just always map your function to anything, I can't really work with anything. Because when it's anything, you know nothing about it.
That's true. You can't really check your work as well. See if, hey, it should be within this domain, and it goes out of the domain, and it's probably you're made a mistake or something.
Right, you can't reason about it. The more general the output, the less you can say about it, the less you can reason about it. So knowing what the output is very useful. Okay, so this, not a function. Because I have one goes to A, one goes to B. Nope, can't have that. If we have it like this, okay, now it is a function. And so now we can use our function notation. And we can talk about f of 1 is equal to A. F of 2 is equal to B. Perfectly valid notation. Now, sometimes in our notation, well, we'll get to that sometimes later. Anyway, so that's what this is saying. For every little x in our left-hand set here, in our big X, the set that we're coming from, so all our left-hand element sets, for any little x in there, there has to exist a unique y such that x is paired with y, or f of x equals y. Thing to the right of little x is y. We call the big X here the domain, we call the big Y here the codomain, and we call f of the entire set, big X, the image, or the range. So let's make sense of this notation. Because that's f of big X, that's f of that whole thing right there. Let's go back to this example. Where x is the set 1, 2, big X is the set 1, 2, 3. So what does f of big X mean in this context?
I guess it would be ABC. Right?
It would be the set ABC. And so we would call this the image or the range of the function. I'll typically say image.
And this is exactly only the outputs that you will get from the domain.
Correct. So let's change up our function now. Now let's pretend our function mapped everything to little a. Now in this case, f of big X is the set containing little a, which is just now a subset of big Y. It's not all of big Y. So when you see this notation, I didn't put the notation up there? Oh, it's right here. So the way we read this notation, this is how we read it. F is a function from X to Y. This means that we map everything in X to something in Y. X is a domain, Y is a codomain, and then the elements in Y that we actually use, we call the image or the range. So in this concrete example, here's our domain, here's our codomain, but here's our image or our range. So your image or your range is always a subset of your codomain, and it's rare that you ever actually talk about the codomain directly. And so I don't know if you've ever even heard codomain in your classes before. You've probably just heard about the range or the image. Domain and range. For some reason, the more basic textbooks always say range, and the more advanced textbooks always say image. I don't know why. It's a weird pattern. And since I use the language of the more recent textbooks I read, I always say image.
You're the first person I've heard image from. So.
Yeah, I remember that I used to say range all the time. And I used to try to always say range, and it's just impossible because I don't think that much about the words I say. So I just make sure I make that point when I'm teaching a class. I'm going to say image, not range. Sorry. It's dumb that we have two words for it, but we do. All right. So again, when you see this notation, this is crucial notation. Crucial. Of all the stuff we talked about today, understanding this notation is by far the most important thing. Because in topology, there's two things that we're going to be working with over and over again. We're going to be working with direct sets of things and then functions from one set to another set. And so you've got to understand this notation. When you say f is a function from X to Y, you should be thinking, there's a set, f maps everything in here to something in here. So crucial notation.
Okay, so that notation is saying I'm plugging in the
You're plugging in
array
things
of
from
X,
here.
and getting all of the set of Y.
Not all of it, possibly just some of it.
Getting the image.
Your image is a subset of Y. But you should be able to plug anything in here into your function and get something out of it. If X here is 1, 2, 3, and F is a function from X to Y, F better map 1 to something, and 2 to something, and 3 to something. We have to always use all of X. We don't have to use all of Y, that's fine. We have to use all of X. It has to map everything in X to something in Y. Okay, crucial notation. All right, let's see, concrete example here. F, same thing. Okay, same thing. So here's our X, here's our Y, here's F. F is a function from, oh, it switched. All right, let's switch now for this function right here, F. So in this case, big X is equal to the set A, B, C. And big Y is equal to the set 1, 2, 3, 4. Why not? Put a 4 in there. And that, boop, 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 the 4 there. All right. So here's F. Notice F maps everything in X to something in Y. So F is a function from X to Y. Oftentimes it's helpful to draw these things out pictorially and see them pictorially. So here's our set X, it contains A, B, and C in it. Here's our set Y, it contains 1, 2, 3, and 4. And our function F is represented by all the arrows here. And it maps A to 1, B to 2, C to 3. I'll sometimes accidentally call functions a mapping. I'll say F is a function from X to Y, or F maps X to Y. Make sense there? I think it's pretty intuitive terminology when you see it this way. Okay. Cool, cool. All right, definition. If F is a function from X to Y, we've already said a lot right there. If F is a function from X to Y, and big A is a subset of X, then we define F of big A to be the set of all little y's in big Y, such that there exists some little x in big A, such that F of X is equal to, that's what should be a little y, sorry. To little y. And it's saying exactly what you expect. So if I didn't even give you that definition, now if I would come up here and I said, let's call A the set AB. So notice that big A is a subset of big X, right? And if I would have asked you, okay, using this function F, what is F of big A? You probably would have already said the set 1 and 2. That's what this definition is making explicit, doing what we just did. So let's read it again. If F is a function from X to Y, and A is a subset of X, then we define F of A to be the set of all the right-hand elements, all the little y's and big Y's, where there existed some left-hand element, little x in A, such that F of little x was equal to the little y. So it's just collecting up all the right-hand elements that we paired to from the elements in big A. Definition makes sense? One of those definitions where it's easier to understand than it is to read. You understand the idea, but reading it out, it's hard to connect reading it out to the idea. Okay. We already talked about this one, but let's say it again. A function f from x to y is a constant function if and only if, for any x you choose in the domain, it always maps the same thing. So this right here is not a constant function. However, if I would have mapped A to 4, B to 4, C to 4, now it is a constant function. It maps everything to the same thing. So the function is constant if for anything you pick in the domain, what it maps to is just one thing, C. Everything just maps to C, some constant C. I probably should have said there exists a C in Y such that for all x, f of x is equal to C. Sorry, should have specified that this comes from big Y. That wasn't good. But I think you get the idea, right? Cool. All right, identity function. Given some set x, if I give you a set x and I talk about the identity function on x, you instantly know what that function is. It is the function from x to x by identity of x on little x is just little x. In other words, it's a function that always returns whatever you gave it, or it's a function that pairs everything with itself. Notice the identity function is a function from x to x. So if I tell you x now, so ignore y, ignore ABC, whatever. If you just have this set x, in a context, ignore everything else. I just say, here's the set x. Now let's look at identity on x. So in this context, all I said is, here's our big X. Now let's look at its identity function. You instantly know what this is. This is the function that maps little a to little a, little b to little b, little c to little c. Maps everything in big X to itself. So if I give you a set, then we can instantly talk about the identity function on that set. It's just a function that maps everything to itself. So that's what this is saying. So looking up here at our example, if I ask you what's identity x on b, it's just b. What's the thing paired with b on our identity function? B. So that's what this notation is saying. Given some set big X, the identity function from big X to big X is given by the identity function on any little x. It's just that same little x. Whatever its input is also its output. Maps everything to itself. Pairs everything with itself. A bunch of ways of saying the same thing. Good there? Cool. Next. Given a function f from x to y and some little y in big Y, we define its inverse or its preimage. Its preimage. So the image is what it maps to. So the preimage is where it came from.
That's the domain.
It's going to be something in the domain. This is going to be helpful to have a concrete example here. So let's do x, a, b, c like this again. Y, we'll do 1, 2, 3, 4. And f will do a goes to 1, b goes to 2, c goes to 3. So here's a concrete example that we'll use. Now, pick any element out of here. 1. We're saying that the preimage, f inverse of 1, or the preimage of 1, is equal to the set of all things that map to 1. In this case, it's just A. When it's just one thing, sometimes we don't bother writing the set, and we say the preimage of 1 is just A instead of the set containing A. But notice that we could have also had the function A maps to 1, B maps to 1, C maps to 1. If this would have been our function, then now the preimage of 1 is a set containing A, B, C. And what's the preimage of 4? The empty set. So that's what we're defining in this notation. So let's go over it again. Well, now let's go over it explicitly. If f is a function from x to y, and little y is anything in our codomain, so pick anything out of y, we define the f inverse of y, or the preimage of y, I'll say that both ways, f inverse of y, or the preimage of y, to be the set of all little x in the domain, such that it was related to y. So all the things in the domain that were related to y. Similarly, if we have w as a subset of y over here, then its preimage is a set of all things related to some element in w. And again, that's one of the things that you probably would just guess now. without actually writing this. So let's switch this up one more time. A goes to 1, B goes to 1, C goes to 2. So we'll have this function. What's the preimage of 1? The set containing AB. What's the preimage of 2? The set containing C. Sometimes we'll just write it as C when it's just one element out of laziness. And then finally, what's the preimage of the set containing 1 and 2?
The set containing A, B, C.
Yeah, in this case, it's equal to all of X, the set containing A, B, and C. Because you're looking at everything that mapped to 1 or mapped to 2. Everything that mapped to 1, that gives us A and B. Everything that mapped to 2, that gives us C. Does that make sense? Remember, big X here is just shorthand for the set ABC. That's what big X was.
Okay, so we're kind of getting lazy. For instance, there's really saying set.
We can do it both ways.
Oh,
We have both notations defined now. We can talk about the preimage of an individual element, which is what we were doing right here. Or we can talk about the preimage of some subset of Y. And now they're both defined. And they both give you exactly what you expect. They give you sets. Sometimes we're lazy when the set contains just one element and just write the one element. Okay. Question. Suppose now you don't know anything about your X, you don't know anything about your Y. All you know is that F is a function from X to Y. You have no clue what are in the sets X and Y. You just know F maps from X to Y. Question. What is the preimage of Y equal to?
I was going to say X, but then there might be some...
There might be some things in X that never got mapped to something in Y, right?
Exactly.
No. What does it mean for F to be a function from X to Y? It means it maps everything in X to something in Y. So the preimage of Y is always X. That is always true. However, the image of X is not always Y. We don't have to map to all of Y, but we definitely have to map from all of X. We map everything in X to something in Y. That's going to come back to bite 100 times. This notation says so much in one go.
Okay, so if I just plug in a random value as an inverse value, and obviously it doesn't exist in the domain, then it would just return an empty set.
Correct.
Okay, that makes sense.
Cool. So if that makes sense, then I think you did. Most crucial thing out of all this so far is just getting this notation. All right, a bunch of examples. Let's see what I did. So X now is a set A, B, C, D. Y is a set 1, 2, 3, 4, 5. A here, notice, is a subset of X. And B, notice, is a subset of Y. So just setting up a bunch of stuff so that we can reference it down here. And now I define F as a function from X to Y by F is equal to this function. We map A to 1, B to 2, C to 4, D to 4. First off, is this a function? Or did I cheat? It's a function. A only goes to one thing. B only goes to one thing. C only goes to one thing. D only goes to one thing. We're good. I didn't have C goes to 4 and C goes to 3. Otherwise, we'd be in trouble. All right, so let's get comfortable with this notation. What is F of little a? It's just 1. Remember, this was shorthand for what is the right-hand element of this thing. is 1. What's f of b? 2. F of c and f of d. Wonderful. Let's look at the preimage. What's the preimage of 1? A. The set containing A, but since it's one element, we'll just write A. What's the preimage of 2? B. What's the preimage of 3? Empty set. What's the preimage of 4? The set containing C and D. What's the preimage of 5? Empty set. Let's try one more question. What is f of E? Undefined. Bad question. Bad question. This notation is only defined where that thing comes from our domain. On the other hand, if we would have said this, what is f inverse of 6? This is just still undefined. 6 is not in Y. Preimage notation only makes sense when you grab elements out of our codomain. So it's okay if the preimage is the empty set, but that doesn't mean you can go pick any old thing you want and plug it in for the preimage. It has to come from the codomain, otherwise this isn't defined. Notice that over here we always said little y comes from big Y when we were talking about the preimage, or when we were talking about the preimage of the set W, it was a subset of Y. So it's always in reference to the codomain. Okay, so I think that's all the gotchas. Continuing, what's f of big A now? The set containing 1 and 2. The set of everything A mapped to, A only mapped to 1. And the set of everything B mapped to, B only mapped to 2. What's the preimage of B? The set containing C and D. Those were the only things that mapped to either 3 or 4 or 5. Wonderful. Now, X is a defined set, so what's the identity on X?
The set of ordered pairs, A, comma A, B, comma B.
It's the function that maps A to A, B to B. Is that my phone? C to C. Just want to make sure it didn't stop the recording. D to D. Okay. So that's the identity on X. Notice that when you're given a set, you instantly know the identity function associated with that set. Here's why. That's a set. So we instantly know what the identity function on Y means. That's a function that maps 1 to 1, 2 to 2, 3 to 3. Sorry, my handwriting's getting lazier and lazier. 4 to 4, and 5 to 5. That makes sense? All right, we've regurgitated a ton of notation on you. Hopefully you feel kind of comfortable with it right now. Move on to the next thing. Okay, notation for how we write functions. So sometimes we have these functions, and they're infinite functions. Here's an example of a function we might care about. It maps 0 to 0, it maps 1 to 1, it maps 2 to 4, it maps 3 to 9, it maps 1/2 to 1/4, it maps negative 1/3 to 1/9, it maps negative the square root of 2 to 2. What's the pattern here?
The right-hand element is the left-hand element squared.
Yeah, we're mapping every number to itself squared. What's 0 squared? 0. What's 1 squared? 1. What's 2 squared? 4. What's 3 squared? 9. What's 1/2 times 1/2? 1/4. What's negative 1/3 times negative 1/3? 1/9. What's negative square root of 2 times negative square root of 2? 2, etc. Write these out for every real number. We can't write them out for every real number. It's an infinite set. That'd be very tedious to do. So we need a shorthand for talking about functions like this, these infinite functions. Because this is a very natural function. I want to square every number. That's something we do all the time. So it'd be nice if we had a better way of writing this out. Now we can use our set builder notation. We could have said f is all the ordered pairs x, y. where x and y are real numbers, and y is equal to x squared. The right-hand element is equal to the left-hand element squared. This gives us this exact same set. You see how it gives us the same thing? Remember that r is just fancy symbol for a number, but we know we're talking about numbers. So x is in the real numbers, or in other words, x is a real number, y is a real number. And y, the right-hand element, is equal to x squared, the left-hand element squared. So here's one way that we could write this function. Still, kind of a tedious way. Another way we could have written that function, we could have said f is a function from r to r. It maps everything in r to something in r by, what do we map the left-hand element to? Itself squared. F of x is equal to x squared. Now, when you did algebra courses, all your functions were from the real numbers to the real numbers. So in your algebra course, your book just wrote f of x is equal to x squared. And it was understood that f maps from the real numbers to the real numbers. And your textbook didn't bother making that explicit, because you were never working with functions that did anything different. If your textbook was a little bit more precise, it would have used this exact notation. F is a function from the real numbers to the real numbers by f of x equals x squared. So that's our shorthand for writing these infinite functions. Very convenient shorthand. So when you see f of x is equal to x squared, it's instantly understood what we're talking about. We're talking about the function that maps every left-hand element to itself squared. The right-hand element is always the left-hand element squared. The right-hand element is always the left-hand element squared. What's the right-hand element of x? It's just x squared. What's the right-hand element of 1? 1 squared. What's the right-hand element of 2? 2 squared. What's the right-hand element of 3? 3 squared. Whatever you plug in for your x here, it tells you the associated y. Whatever you plug in for your left-hand element, it tells you the associated right-hand element as a calculation. If I wanted the function that mapped every number to the number 1 greater than it, so I want to map 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. How would we do that? I would say f is a function from the real numbers to the real numbers by f of x is equal to just itself plus 1. That would map 2 to 3, 3 to 4, 4 to 5. We'd map pi to 4.14159, right? So that gives us functions. And the typical notation that we'll use for functions. Typically, we talk about functions from the real numbers to the real numbers in a way like this. Very common functions. And no doubt, the types of functions you've actually had the most experience with. Okay. Now some theorems. We're not going to prove any of these, but I want to give examples to at least make it appeal to your intuition. And I have some examples written down here, so we'll have to think too much on the fly, I guess. Okay, so if f is a function from x to y, that means f maps everything in x to something in y. And a is a subset of x, b is a subset of x, u is a subset of y, v is a subset of y. Notice I use letters at the start of the alphabet for subsets of x, and letters at the end of the alphabet for subsets of y. Common pattern. Then, all this is true. And we'll go over each one, make it appeal to the intuition. But keep in mind, so that we don't have to keep saying it over and over again. A, that's a subset of the domain. B is a subset of the domain. U is a subset of the codomain. V is a subset of the codomain. Okay. So first one. F of A union B is equal to f of A union with f of B. If I take A and B, remember A and B are subsets of the domain, and I union them together first, and then I do the mapping, that's the same as first mapping A and mapping B, and then unioning the result together. So, don't want to prove any of these, but I want to walk you through these two examples. So here's going to be our two example functions. F is going to be the function, f of x is equal to x squared. It's understood that we're going from the real numbers to the real numbers. A is going to be the numbers from 0 to 2, including 0 and 2. So this is our interval notation. Remind you of that interval notation. This is an infinite set of numbers, including all the numbers between 0 and 1 and 0 and 2. including 0 and 2 themselves. 1.15976 is in here. Pi halves is in here. Square root of 2 is in here. Okay, B is all the numbers from 1 to 3, including 1 to 3. We'll forget U and V for now. Notice all the ones over here are going to use A and B. All the ones over here are going to use U and V. So now let's make sense out of this. So F is going to be x squared. What is F of A? Well, first off, here, let me just erase this example altogether. We'll use this as our scribble space. So first off, let's see, what is A union B?
That's the set from 0 to 3.
The set from 0 to 3. A is all the numbers from 0 to 2. B is all the numbers from 1 to 3. Take all the numbers that are between 0 and 2, or between 1 and 3. You get all the numbers between 0 and 3. Okay. So now, what is f of, remember f is our x squared function. So what is f of, let's just make sure we're all on the same page here. What's f of 1/4? 1/16. 1/4 times 1/4. 1/16. Right? So what is f of 0?
Oh, no, it's in there.
0. It's squaring the number. So f of 0 is 0. What's f of 1? 1. What's f of 3/2? 9/4. Finally, what's f of 3? 9. So now, if we were to plug in all the numbers into this function, would it help to graph this thing? I don't know. Maybe it would, maybe it won't. I don't know if I want to talk about graphing, because that'll be more confusing. Okay, so here's plugging in a bunch of numbers. What if we were to plug in now all the numbers from 0 to 3? What are all the possible numbers this would spit out?
All the set from 0 to 9.
It would spit out all the numbers from 0 to 9. Get any number between 0 and 9, take its square root. That's going to be a number between 0 and 3. Okay, so in this case, f of A union B was equal to 0 to 9. Right? Now let's instead look at just f of A. What would that be? If we plug in all the numbers from 0 to 2, what would we get as our output? All the numbers from 0 to 4. If we plugged in all the numbers from 1 to 3, what will we get? 1 to 9. Now, if we union up all the numbers between 0 and 4 and 1 and 9, what do we get? 0 to 9. So f of A union f of B is the same thing as f of A union B. Here with that example, let's look at our second function, g. What does g do? It maps 1 to 1 and 2 to 1. Let's see. A's 1, B's 2. So first off, what is g of A union B equal to? A is the second containing 1, B is the second containing 2. It's just equal to the second containing 1. Right? What is g of A equal to? Well, it's everything that 1 maps to using this function. The second containing 1. What's everything that B maps to? Second containing 1. So notice that G of A union G of B is the same thing as G of A union B. So it worked in both cases. All right. There's this first one. Now let's go to the next one. The next one says f of A intersect B is just a subset of f of A intersect f of B. In other words, the mapping of the intersection is a subset of the intersection of the mappings. So maybe it's equal, maybe it's not. Let's see. Starting with f, is this going to be equal? So this time we're looking at intersect. And first off, what is A intersect B? We're still using, remember, we're talking about the f now. So the f is going to be f of x equals x squared. A is 0 to 2, b is 1 to 3. So what's the intersection of 0 to 2 and 1 to 3? So we're looking at all the numbers from 0 to 2 and 1 to 3. Yeah, all the numbers that are both between 0 and 2 and between 1 and 3 are all the numbers right here, between 1 and 2. So A intersect B is all the numbers from 1 to 2. Those are the only numbers that are going to be in both A and in B. Make sense? Okay, so now what is f of A intersect B? 1 to 4. It's going to be all the numbers between 1 and 4, including 1 and 4. What is f of A? A is the set. So it's still just 0 to 4. What is f of B? Still just 1 to 9. Now, what is the intersection between 0 and 4 and 1 and 9? It's still going to be 1 and 4. So in this case, f of A intersect B is the same thing as the intersection. Maybe write one more line here. Let's look at f of A intersect f of B. In this case, it was equal to 1 to 4. So they gave us the same thing. So there's an example where it was equal. Now in the next example, hopefully I picked one where it's not equal. Maybe I'll do my g's over here. So, no, that would be too confusing because it's still A's and B's. All right, so now looking at this, what is G of A intersect B? What is A intersect B? Is that too hard to see? Maybe I'll just do a divider here. So over here, A is equal to the set containing 1, B is equal to the set containing 2, and G is equal to the set that maps 1 to 1 and 2 to 1. That's what we're looking at. Okay, so what is A intersect B? The empty set. So what is G of A intersect B equal to? The empty set. What does the empty set map to? Maps to nothing. Maps to the empty set. However, what is G of A? The set containing 1. What is G of B? The set containing 1. What is the set containing 1 intersected with the set containing 1? the set containing 1. It's just a cell. So in that case, notice G of A intersect B was the empty set, but G of A intersect G of B was the set containing 1. So the empty set is a subset of the set containing 1. So that's an example where we get is a subset but not equal to. So I gave you one of each. Good there? And gives you a hint about where we get the problems. Where we get the problems to a bunch of these ones that aren't equal is where we have two left-hand elements mapped to the same right-hand element. That's where we can get in trouble. Okay.
You're saying that's when you start becoming equivalent.
It's when you can potentially get them not equal anymore.
Okay, when they're, yeah.
All right. Let's look at the next one. What does the next one say? It says f of A minus B is a subset of f of A minus f of B. Let's set it up again over here. So this time we're doing minus here, minus here. Maybe right up here, what is A minus B? So
0 to 1, not including 1.
A is all the numbers from 0 to 2. B is all the numbers from 1 to 3. So if I start out with all the numbers between 0 and 2, and I get rid of all the numbers between 1 and 3, what am I left with? All the numbers from 0 to 1, not including 1. So A minus B is all the numbers from 0 to 1, not including 1. Because 1 was in B, so we got rid of it. Okay. So now, what is f of A minus B? The squaring function. It's just going to be all the numbers from 0 to 1, not including 1. Right? Now, once again, f of A is still just 0 to 4. F of B is still just 1 to 9. That doesn't change. What is f of A minus f of B? What is this minus this? Take all the numbers between 0 and 4. Now get rid of all the numbers between 1 and 9.
I would say 49, not including.
It's just 0 to 1. We start out with all the numbers between 1 and 4. And now we got rid of all the numbers between 1 and 9.
Oh, yeah.
You start with 0 to 4 and then got rid of.
I start with this, and I get rid of that. I'm doing f of A minus f of B. Imagine I got all the people on Earth whose age is between 0 and 4. And now I get rid of everyone in that category who's 1 year old or older, or between the ages of 1 and 9. What am I left with? I'm left with all the kids who are from 0 to 1, not including 1. Once you reach your first birthday, well, we chuck you out. You were in there. So in this case, it was equal. Surprise. All right. What about in this other case? A is equal to 1, B is equal to 2. G is a function that maps 1 to 1 and 2 to 1. So we're doing minus here. So first off, what is A minus B? The set containing 1. What's G of the set containing 1? It's just a set containing 1. See that? Now, what is G of A equal to? The set containing 1. What is G of B equal to? The set containing 1. What's G of A minus G of B? The empty set. So, I wrote it backwards. Should I just switch the sign? Is that too confusing? We haven't written subsets this way before, but we'll pretend that's fine. F of A minus F of B is a subset of F of A minus B. Can't believe I wrote that backwards. Wonder if I have that backwards in my notes. you need to put a little star next to it. Da, 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 da. No, no. Functions. No, I have it right in my notes. I just wrote it wrong up there. Did I write this one correct? Oh, it's equal, so it doesn't matter. Okay. So subset goes that way. This was a subset of this. Over here, when we were using this function g down here, g of a minus g of b was the empty set. G of a minus b was the set containing 1. Right? So I gave this an example where we had subset. Okay. Now, let's go look at the preimage ones. Preimage ones, I don't know how. Preimage ones just maintains them all equal. I don't know how much time I want to spend on this. You want to plug it into examples, or you just want to keep going? Maybe preimage is good to do with some of these, just because make you think about it. So we won't bother with the G this time. We'll just stick with the F. And I think this will be good. Okay, so what we're going to have to use over and over again is the preimage of U and the preimage of V. So first off, we're going to be looking at U union V. We're going to figure out what that is. Then we're going to look at the preimage of U union V. We're going to look at the preimage of U. We're going to look at the preimage of V. And then we're going to look at the preimage of U union the preimage of V. Okay. Let's select a little bit more. U union V. Okay. So here's our U, here's our V. U 0 to 4, V is 1 to 9. What's the preimage of U? Oh, sorry. Sorry. This one first. What's U union V?
0 to 9.
0 to 9. We just union these two sets together. If I take all the kids who are between the age of 0 and 4, or between the age of 1 and 9, I take all the kids whose age is between 0 and 9. Okay. Now let's look at their preimage of all the numbers between 0 and 9. What are all the numbers I can get such that when I square them, I get a number between 0 and 9? Let's see. 0 squared is 0, so that's between 0 and 9. 1 squared is in there. 1 squared is 1, so it's in the preimage. 2 squared is 4, which is in there, so it's in the preimage. 3 squared is 9, so it's in there. What's 4 squared? 16. So 4 is not in the preimage because it maps to 16, which is outside this set. So we're looking for all the numbers such that when we square them, we get 0 to 9. So you're saying 0 to 3. It's all the numbers from 0 to 3. Those are all the numbers such that when we square them, we get a number between 0 and 9. Right? Don't disappoint me.
Oh, no. It's negative 3 to 3.
Negative 3 to 3. What's negative 3 squared?
9.
Negative 3 squared is 9. Negative 2 squared is 4. Negative 1 squared is 1. Negative 1/2 squared is 1/4. So these are all the numbers that are the preimage of 0 to 9. Negative 3 to 3. Okay. What's the preimage of U?
Negative 2 to 3.
U is 0 to 4. What are all the numbers I give as 0 to 4? Negative 2 to 2. Those are all the numbers such that when you square it, you get a number between 0 and 4. What's the preimage of V? Whew.
Negative 3 to negative 1 and union 1 to 3.
Negative 3 to negative 1. Union with 1 to 3. Perfectly valid way to write it. If we need to write it as two intervals, big whoop. That's a set, that's a set. Union them together, that's a set. We're still just writing sets. So take any number between -3 and -1, or between 1 and 3, and when you square it, you'll get a number between 1 and 9. We can't include a number like 0, because 0 squared is 0, and that is not a number between 1 and 9. So we had to skip all the numbers from -1 to +1. All right. And now, what's the preimage of U union with the preimage of V? So we're taking all the numbers that are either between -1 and 3, or -3 and -1, or between -2 and 2, or between 1 and 3. And what are we left with? So we're unioning this with this with this. We're doing the preimage of U union with the preimage of V. So we're unioning this set with this set.
Same as the previous one.
It's just all the numbers from -3 to 3.
Hold on. Okay, and it's also including -1 to 1. Yep.
Yeah, because -1 to 1 is captured in here.
It is.
And when you union, it just has to show up in one of the sets. So we're talking about everything in this set, or in this set, or in this set. If you're in one of those sets, you show up in the union of those sets. Cool. Let's switch to intersection. 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 That will be the same. That will be the same. Intersection. Get rid of that. Get rid of that. Get rid of that. Get rid of that. Well, we'll see how we need to write these. Okay, what's U intersect V? Looking over here, U is 0 to 4, V is 1 to 9. We're talking about everyone who's between the ages of 0 and 4 and between the ages of 1 and 9.
1 to 4.
That's everyone who's between the ages of 1 and 4. Everyone who's between the ages of 0 and 4 and between the ages of 1 and 9.
How come 0's not included in there?
0 is not between 1 and 9. We're doing and now. You have to be both. So 0 isn't in there, 1/2 isn't in there, 5/9 isn't in there. Okay, so there's the intersection, 1 to 4. What's the preimage of 1 to 4? What are all the numbers such that when we square it, we get a number between 1 and 4?
-1.
1 to 2. Yeah. Any numbers between -2 and -1, or between 1 and 2, when you square it, you'll get a number between 1 and 4. Perfect. Preimage of U, that's still the same thing. Doesn't matter that we switched unions to intersections. Preimage of V, that's still the same thing. Now let's look at the preimage of U intersect the preimage of V. So we're looking at everything that's in this or this and this.
-2 to -1.
Right, where this intersects this gives us -2 to -1. And then where this intersects this piece gives us 1 to 2. And it gave us the exact same thing. All right, and then, I don't know. I don't think there's much value in doing the subtraction one. I think you get it, right?
Is there a special type of function, something where output is always, where there is no domain X that also outputs the same Y? As another element.
You are describing a what we call a one-to-one function. You guys may want to resituate yourselves. I didn't realize how bad that orange was getting until I backed up and realized I need to switch to red. So, sorry about the bright orange. And if it gets to the point that you just can't read it, let me know. I think when the marker was good, it's okay, and then eventually dies out pretty bad. All right. So once again, new definition. And this tense notation, that's never ever going away. Got to get comfortable with it. Let f be a function from x to y. What does that mean? It means it maps everything in x to something in y. F is a function from x, y. So let f be a function from x to y. Then it is one-to-one if and only if two outputs are the same implies their inputs are the same. So remember, it's a function if it maps every left-hand element to only one right-hand element. It's a one-to-one function if every right-hand element comes from only one left-hand element. So if two right-hand elements are the same, then the thing that they came from better be the same. In other words, they didn't come from two different inputs. If the outputs are the same, the inputs better be the same. Otherwise, it's not one-to-one. If I can get the outputs the same from two different inputs, then it's not one-to-one. It's still a function, just not one-to-one. So that's what it means for a function to be one-to-one. On2 is pretty simple. A function is on2 if its image or its range is all of y. So when you see this notation, f is a function from x to y, this means it maps everything in x to something in y. If I tell you, oh, it's also on2, that means it maps everything in x to everything in y. It used up all of y. If it uses up all of y, we call it an onto function. And then we call it a bijective function, or a bijection, if and only if it's both one-to-one and onto. So in a bijection, we map all of x to all of y, and everything in x maps to one and only one thing in y, and everything in y was mapped to from one and only one thing in x. So it's a perfect pairing off of everything. And we use up everything in both sets. That's what a bijection is. Okay, let's look at some examples. Let f be a function from the real numbers to the real numbers by f of x is equal to x squared. Question, is this function, here's how we write one-to-one. 1-1, one-to-one. Because, right, spelling it out takes forever. So we won't be doing 1 to 1 anymore. We'll just write 1-1. That's one-to-one. If I'm asking if a function's 1 minus 1, then I probably shouldn't be teaching the class. Okay. So, this function, f of x equals x squared, is it a one-to-one function?
It's only because negative 2 is
Yeah, it's not one-to-one. If we were to write out this function, f, explicitly, we can't because it has infinite things in it, obviously. But somewhere along the lines, we would have written negative 2. And what does negative 2 pair with? 4. And then we would have gone on writing, and eventually we would have written out 2. And what does 2 pair with? 4. So since I have two left-hand elements, two different left-hand elements pairing to the same right-hand element, then it's not one-to-one. Or, using our definition that we have up here, the way I would have said it, is I would have said, notice, f of 2 is equal to f of negative 2, but 2 is not equal to negative 2. So here's my a and b. Notice that f of a equals f of b, but a is not equal to b. So it's not one-to-one. It's only one-to-one if outputs being equal implies inputs are equal. Here I found two things, different inputs, given the same output. Can't happen if it's one-to-one. All right, next question. Is it on 2? In other words, do we map to everything in big R over here? Do we map to every real number? No. What are we missing? We're only missing one number, negative 17. You can't find a number such that when you square it, you get negative 17. Wait, what about negative 16? What times what gives me negative 16? Well, 4 times 4, that gave us 16. But negative 4 times negative 4, that gives me negative 16, right? No, it just gives me 16. I can't take a number and square it and get a negative number out of it. If the number I square is positive, that's a positive number. If the number I square is 0, that's 0. If the number I square is a negative number, that's a positive number. So I can't square a number and get negative out of it. So what is the image or the range of this whole function? If this is our function, what is f of all of r equal to? It's equal to all the numbers from 0 to infinity, which is only half the real numbers, right? Well, a little bit more than half since we included 0. That's a joke. You can't talk about half of infinities. Doesn't make sense. You can't talk about some infinities being bigger than others. We can do it as a side conversation. I don't know. You guys interested in that?
Sure.
Because we can do that right now to give you a sense of these infinities. So we have to talk about what it means for two sets to be isomorphic to each other, or in other words, to have the same size. Two sets have the same size. How would you naively determine if two sets have the same size? The naive way is to count them, right? If I were to have a room full of boys and girls, and I ask you, are there the same amount of boys as there are girls? The naive way to do it would be to go and count all the boys and go and count all the girls and see if you get the same number. But there's a much simpler way to do it. You say pair up. Boys and girls pair up. Now I don't need to count them. I just need to make sure, did anyone get left out or did we pair them all up? If I pair them all up, I know that there's the same amount of boys and girls, and I don't need to know how many there are. So you can do a similar thing with infinities. If I can pair up two infinities, and I match every number with one and only one number, then they must have been the same size. Even though I can't really count infinity. How do you count infinity? So this pairing up is what we mean when we say two sets are the same size. Can you do this pairing up between them? Or can you create a bijection between them? Can I map every boy with one and only one girl, and every girl with one and only one boy? Can I create a bijection between the set of all boys and the set of all girls? If I can, then the two sets are the same size. If I can't, then the two sets are not the same size. So that's how we check if two sets are the same size. We don't count them because sometimes the set's infinite, so that's a dumb thing to do. So we have to come up with a different way. So that's what we do. We see if can we create a bijection between the two sets. Create a bijection between the two sets have to be the same size. And that's what it means for two sets to be isomorphic. They have the same size, so they're in some sense the same. Sets isomorphic, or sets being the same size, would be an equivalent relation. In set theory, it's what we care about for equivalent. Two sets are equivalent if they have the same size. So now I'm going to show you that the naturals are the same size as the integers. Should we attach a little narrative to it? We'll do a little narrative to it. Because this is a question that bothered me clear back when I was in 6th grade, or 5th grade, or whenever it was. I was in Beverly's class. And she says, I have a question for you. If you take an even and you add them together, you get an even. If you take an odd and you add them together, you also get an even. But if you take an even and an odd and you add them together, you get an odd. So there's two ways to create an even, one way to create an odd. So why aren't there twice as many evens as odds? That's the question she asked me. And so I explained it to her, no, there's two ways to create an odd. You can do an even plus an even, that's even. You can do an even plus an odd, that's odd. You can do an odd plus an even, that's also odd. You can do an odd plus an odd, that's also odd. So two ways to create an even, two ways to create an odd. So there should be just as many even integers as there are odd integers. Now I gotta think about it. Wait a second, are they the same number? Because let's think about the positive integers, right? You have 1, 2, 3, 4, 5, 6, 7, 8. For every odd, you have an even. So if you start at 1, then it seems like you have the same number of even and odds, right? 1 has 2, 3 has 4, 5 has 6, 7 has 8. Now let's look at the negatives. -1, -2, -3, -4, -5, -6, -7, -8. So if you look at the positive integers, same number of evens and odds. If you look at negatives, same number of even and odds, but 0 is even. So doesn't that mean that there's one more even than odds? Is that maybe I cheated with my parent. Because you start with an odd when you look at the positive integers. You know 1, and then 2, 3. So maybe we do 1, and then you have 2, 3, 4, 5, 6, 7. And since it starts with an odd, maybe when you look at the positive integers, there's actually one more odd than even. But then when you look at the negative integers, you would also have one more odd than even. So that's 2 more odds than even. But then 0 is even, so then you get one more odd than even. So is there one more even than odd or one more odd than even? That's a question that bugged me. And I figured out the answer. Bad question. There's the same number of evens and odds, but this way of thinking about it is a very elementary way of thinking about the problem, which is appropriate since I was in elementary school. So there, a little narrative to go with the problem. So now what I'm going to show you is actually there's the same number of natural numbers, 0, 1, 2, 3, 4, 5, as there are integers. Your gut is probably, no, there's roughly half as many natural numbers as integers, right? Let me show you that half doesn't make sense when we're talking about infinities. So I'm going to show you that the natural numbers and the integers are the exact same size. And the way I'm going to do this is I'm going to create a bijection from the naturals to the integers, and then map every natural to one and only one integer. Now, hopefully I can do this on the fly. Don't make a mess of it. But what am I doing? I am creating, why did I pick up the orange again? Oops, the one that was dying on me.
Are your naturals starting at 0 or 1?
I'll start at 0, but it doesn't matter. Just because that's how I think about naturals. So we're doing f from the naturals to the integers, and I need to do it in a one-to-one and onto way. I need to create a bijection. Here's what I'm going to do. Might need to play with it and mess with it a little, but we'll take a shot in the dark. Right to the left a little bit here. Average right over there. I'm going to say f of n is equal to n over 2 if n is even, and n plus 1 over 2, or am I going to want to do minus 1? Negative n plus 1 over 2 if n is odd. All right, let's play with my function. Let's see what everything maps to. So we'll just create a kind of table here. So over here, I'm going to create my naturals, my inputs. I'm going to see what they map to. Over here is going to be my n. Over there, f of n. And my n is going to be all the naturals. So I'm going to map 0 to something 1, 2, 3, 4, 5. And we'll see what they each map to. So using this mapping, what does 0 map to? Well, if 0 is even, we use this mapping. If 0 is odd, we use this mapping. Perfectly valid way to define a function. So, plug in 0 for n. 0 is even, so let's see. Then we do 0 divided by 2. What's 0 divided by 2? 0. So, 0 maps to 0. Okay, what about 1? Is 1 even or odd? Odd. So 1 plus 1 is? Divided by 2 is? Make it negative. So 1 maps to negative 1. What does 2 map to? Well, is 2 even or odd? It's even. So 2 divided by 2 is 1. Okay, 3. Is 3 even or odd? It's odd, so we do it down here. 3 plus 1 is 4. Divided by 2 is 2. Make it negative. And 3 goes to negative 2. And you'll notice 4 goes to 2. And 5 goes to negative 3. And 6 goes to 3. And 7 goes to negative 4. And 8 goes to 4. Pick any integer you want, and I map to it. I map to every single integer. I map to this whole set. Pick anything in that set, I map to it. Doesn't matter how absurdly massive a number you pick here. I can tell you the number that you plug in to get that number. So I eventually map to every single one. And I do it in a one-to-one way. 1 is the only number that maps to -1. There's no other number that maps to -1. I can write out the full proof of this, but I think it'll just be kind of technical, kind of annoying. And I think getting the ideas is the more satisfying part. So there we go. I created this function, which is a bijection, a one-to-one pairing. I took every natural number and I paired it with one and only one integer. And so they're all paired up. And so there's exactly as many. It's not really the language we use. The language we use is they have the same cardinality. Cardinality is what we mean by size of the sets. The cardinality of the naturals is the same as the cardinality of the integers. And it turns out, I don't know if that one's worth doing. I could walk you through the proof idea if you care. It turns out it's also, so the way that we say this is we say the cardinality, we use absolute value sign for the cardinality. The cardinality of the naturals is equal to the cardinality of the integers. And it turns out it's also equal to the cardinality of the rationals. Surprisingly enough. All the possible fractions you can make. All the possible fractions you can make, still the same number as just the naturals.
Not the irrational.
But not the irrationals. That's a whole new infinity. And we can also prove that if you want. we did this in computation theory. So there's the same number of naturals as there are integers. And also the same number of naturals as there are evens, and also the same number of naturals as there are odds. Those are all the same infinity. We call that the countable infinity.
So 0 to infinity and negative infinity have the same cardinality.
If you're talking about integers, yeah. Yeah, because I could have easily mapped all the negative integers to all the integers, or whatever you wanted. So there's an example of that. Kind of off topic, but I always think that's cool to get a sense for infinities. And yeah, by the time we're talking about the real numbers, it's a whole new infinity. And we prove that in computation theory. And the way that we proved it in computation theory is we proved that there is no bijection you can create from the naturals to the reals. We showed that anytime you had a bijection, you would have missed a number, no matter what your bijection was. So no such bijection exists. We did proof by contradiction. Okay. Anyways. Walk you through an actual way that we formally prove this now. Prove something's a bijection, we're going to do it on a much simpler function. I'm going to prove that 3x plus 1 is a bijection. So what does this function do in words? It pairs every number with 3 times that number plus 1. So I'm taking the number, making it 3 times bigger, and adding 1. That's my function. I'm going to show that this is bijection. It maps every real number to one and only one real number. And it uses up all the real numbers in the image. Not sure which I prove first. First, let's prove it's one-to-one. I'm going to prove that if 2 numbers map to the same output, then those 2 numbers were actually the same input. If you have 2 inputs that map to the same number, then the inputs were equal. So let A and B be any 2 inputs such that they have equal outputs. I'm going to prove that if they had equal outputs, then the inputs had to be equal. You couldn't have gotten equal outputs with different inputs. The outputs are equal, the inputs were equal. That's what we're proving. So assume that A and B are 2 real numbers such that they have the same output. F of A is equal to F of B. But what is F of A looking at this function? It's just 3A plus 1. Just what you get when you plug A into this function. Maybe let's play with this function a little bit. Let's write out the function over here, in case it's hard to read. F of x is equal to 3x plus 1. What is f of 2 equal to? It's equal to 3 times 2 plus 1. We just replace the x with 2. In this case, 7. So what is f of a equal to? It's just equal to 3a plus 1. Whatever a is, it's just 3 of them plus 1. Make sense? So f of a is just 3a plus 1. And f of b is just 3b plus 1. So if f of a is equal to f of b, then 3a plus 1 is equal to 3b plus 1. Right? Now, subtract 1 from both sides. And so I get 3a is equal to 3b. Now it divides both sides by 3. I get a is equal to b. Notice those are my inputs. I just showed if my outputs are equal, then my inputs are equal. So, if two outputs are the same, then their inputs were the same. So we don't have the same output coming from two different inputs. Anytime the outputs were the same, the inputs had to be the same. We can never have the same outputs coming from two different inputs. They always have to be the same. So that's how we show one-to-one formally. The formal proof. Yeah, maybe I should have spent more time on graphing. I don't know.
You should just draw a figure. If you don't put numbers.
But then you have to kind of explain what it is if you're not used to seeing graphs. So there's the formal way that we prove it, that a function is one-to-one. Now, how do we prove that a function is onto? What does it mean for a function to be onto? It means that we use up this entire right-hand set. We map everything in here to everything in here. It means no matter what you pick in here, no matter what you pick in the codomain, I can always find something in the domain that maps to it. So that's how we're going to do this one. I'm going to say, pick whatever y you want. I'm going to find you the x that maps to that y. Let's do this as a concrete example first. So concretely, give me any y you want, any real number. My job is to come up with the x that maps to it using our function. So our function is f of x is equal to 3x plus y. I'm saying pick any output you want. I can always find an input that maps to it. 10, she's picking nice ones for me. She's thinking ahead. She says, find the input that spits out 10. I say easy, 3. If I plug in 3 for x, it spits out 10. Now let's try a harder one. How about 197.614? Right? Let's make a mess for ourselves. Let's say I want my y to be 179.281. Okay, find the x that maps to that. Smart guy. That's my job. I need to find the x that maps to that. So I need to find the number such that when I plug it in here, I get this number out. You with me? So I need to find the x such that 3 of that x plus 1 is equal to 179.281. Subtract 1 from both sides. That's when 3x is equal to 179.281 minus 1, right? And now divide both sides by 3. And so my x is going to be equal to 179.281 minus 1 divided by 3. That's the x, such that if I plug it in to my function, it would give me out 179.281. Now we just need to make sure that this is a number. Let's see, is 179.281 a number? Yes. Is a number subtract a number always a number? Yes. Is a number divided by 3 always a number? Yes. So x is a number. And we can plug it into our calculator and figure out what that number is, or some decimal approximation of it. But there's the x. So for any y you choose, the way I calculate my x is I just put your y right here. I say y minus 1 divided by 3. That's the x that would get that y. Because it'd be the same formula. You plug it in here, subtract 1 from it, divide by 3 for any y you choose.
It's a little confusing because you're switching the variables. It would seem like that would be the y by
179.281. So let's go back. Try and be super clear about this. I'm saying pick any y you want out of the codomain. My job is to find the x that maps to it. What am I trying to show? I'm trying to show that we map to every number. So no matter what number you choose, what y you choose, I'm going to find the x that's paired with it. I'm going to find the x that it's the right-hand element of. If we wrote out all the ordered pairs, what would be the left-hand element that mapped with this thing? Perfect. And so the fact that y was equal to 179.281, that's just particular y. In general, for any y you choose, we're looking for the x such that 3x plus 1 is equal to that y. Or in other words, the x such that 3x is equal to that y minus 1. Or in other words, it's going to be the x that's equal to y minus 1 divided by 3. For any y you choose, I just plug it into there. That gives me the associated x. In the case, Anna said 10. 10 minus 1 is 9. 9 divided by 3 is 3. 3 is a number that if I plug in here, I get 10. Right? So this same thinking is exactly what I'm going to do in my proof. So now, I'm showing it's onto. So I'm going to show that for any little y you pick in the codomain, I can find an x that maps to it. It's going to be that exact same thinking. So let little y be something in R, and observe that we are looking for a little x in the domain R, such that f of x is equal to y. Right? But f of x equals to y, what is f of x? F of x is 3x plus 1, so I'm looking for where 3x plus 1 is equal to y. So that's logically equivalent to 3x is equal to y minus 1, which is logically equivalent to x is equal to y minus 1 divided by 3. But if y is a real number, so is y minus 1 divided by 3. So x is a real number. So I just barely found the real number x that maps to y. So then f of x is equal to f of y minus 1 over 3 is equal to y. Maybe that was over-explaining, and that makes a mess. Let's plug that into the function. So remember, our function is f of x is equal to 3x plus 1. So whatever we plug in, we multiply by 3 and we add 1. So over here I said, notice that f of y minus 1 over 3 is just y. Let's prove that. Let me show that explicitly. Y minus 1 divided by 3. That's what I'm plugging into this function. So I'm replacing my x here with y minus 1 divided by 3. So that's going to be 3 times x plus 1. But, so I have y minus 1 divided by 3 and multiplying it by 3. The 3's go out. So that's just y minus 1. But then I have y minus 1 plus 1, which gives me just y. So here's the x. For any y you give me, here's the x such that f of x is equal to y. That's what I think. Not sure if that just confused it or if that made things click. Cool. So then, f of x, for this particular x, for x equal to y minus 1 over 3, then f of x is equal to, here's f of x is equal to just y. So there did exist some little x in big X. Sorry, that's some little x in big R. Our domain is big R, not big X. These are functions from R to R. So there is some little x in our domain such that f of that little x is equal to y. So in other words, y is in the image of our function, or in other words, big R is a subset of the image of our function, but we know that the image of our function is always a subset of R, so they're equal, so f is onto. We already use this image notation, right? No? Son of a gun. We basically do. Okay. What do I mean by the image of f? What I mean by the image of f is f of the whole domain. Just the image of the function. That's what that notation means. I think we defined it just in terms of logic, not in terms of sets. We should have redid it. So that's what we mean by the image of the function, the domain. So there's shorthand for how you talk about the image of a function. So I showed anything in the image is also, or I showed any real number is also in the image. So the real number is a subset of the image. But I know that the image is already a subset of the real numbers because f maps everything in R to something in R. So my image already has to be a subset of that set. And I just barely showed that that set is a subset of my image, therefore they're equal. Let's say show on to. Okay, So there's an explicit way that we would show a function is bijection. Show us one-to-one and onto. Now let's just make sure we're getting the point here. Another example. This is the function now from R to R squared, or R cross R. So I'm mapping each number in the real numbers to a point, an ordered pair. What's the ordered pair I'm mapping to? The function g of x is equal to the point xx. So 1 maps to the point 1, 1. 1/2 maps to the point 1/2, 1/2. So I'm mapping each number on the real number line, if you want to think about it that way, to an associated point. 1 maps to the point 1, 1. 2 maps to the point 2, 2. 3 maps to the point 3, 3. -1 maps to the point -1, -1. Etc. Okay. Is this function one-to-one? Every point here comes from a single input. The only way to get the point 3, 3 is from 3. Right? Now, is it on 2? No, it is not on 2. We do not get every point in the real number plane. There is no x I can plug in here to get the ordered pair 1, 2. What do I plug in to get 1, 2? If I plug in 1, I get 1, 1. If I plug in 2, I get 2, 2. How do I get 1, 2? I can't. 1, 2 is something in R squared. Remember, R squared is a whole real number plane. But all our outputs are just going to be this line. So we only get that line. Any point on that line we don't get. So it's not on 2. Functions like this get tricky to think about. Function that maps, because it's like mapping from 1 dimension to 2 dimensions. Can you start out a little bit more?
R squared. So all of the
R squared, that was short for, sorry, did we do this notation? It's short for R cross R. Yeah, yeah, simple enough to explain.
Oh, then yeah.
Okay. Almost done. How you guys feeling? Keep going? Burned out? Don't want to exhaust you? I'm happy to keep going as long as you're good. You're tired? All right, we can call. Let's see. We'll be coming back talking about something being a bijection.
I think that's the definition.
Yeah, I just seeing that mentions a definition. I'm just kind of thinking. So maybe next time I'll start with this definition. We can skip the proof, go back from there. That'll probably be good. Okay, sorry. That was more me just thinking. So next week, we're starting Wednesday rather than